E gli altri partecipanti io non li vedo, vedo solamente me.
Sì, stanno arrivando, stanno arrivando.
Ah, ok, quindi li vedrò anche loro nelle finestrine.
Sì, sì, qui si fa nell'oscurità a volte. Io
No, va
sono
bene, perché a volte se
No.
uno parla sembra che parli da solo perché non vede nessuno.
Sì, 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 no, io sono lì, perché a volte la connessione è...
Infatti sono in ufficio, c'è la connessione con il cavo sperando che funzioni.
Anch'io in casa ho la connessione via cavo. Spera che scrivo qui l'email. Aspetta qui. Allora, aspetta. Aspetta. Aspetta, mi sono dimenticato. Ok. Ma vediamo un po' se ci sono degli altri che stanno entrando. Ah sì, aspetta. Ops. Ah, non posso. Già, insieme. Qui c'è José e Gabi, sono anche loro, lavorano nel gruppo tra matematica applicata e biologia. José già lavora nel laboratorio di virologia. Olá, José, aqui para apresentar a professor Timoteo Carletti, José.
Olá, professor.
Ele fala português um pouco, entende?
No, no,
Entende?
I don't speak, I understand Portuguese, but I'm not able to speak Portuguese.
Okay. E Armando, Timoteo, here is Armando Neves from Belo Horizonte, UFRJ.
Hi, nice to meet you.
So we just wait a little bit, 5 minutes, people are arriving. So Timoteo, Armando also works in modeling of epidemics, works in network, game theory also.
Okay.
So he spent some time in Milano, no? Is not? Was a postdoc, Armando?
Yes, and also at Rome for the PhD in Rome.
Yeah. Yeah.
With Galavotti.
Galavotti, wow.
Yes.
Very good teacher.
In fact, a very good guy. I'm not working with those things anymore.
I share an office with Galavotti 2 months in Paris. Yeah. And actually, he was the one that introduced me to the Bureau de Longitude.
Okay.
Yes, he was the one that introduced me to Jacques Lascar, Larchinarius Galabot. Okay, so people are getting. So I had the curious things. Last night I was sending the emails for Timoteo lecture today, and Google thought it was a spam because the mailing list of the course is long. So people thought it was a spam. They blocked my account, and that's so. But then, fortunately, the one of our colleagues is the manager. He reactivated, but it was. Nowadays, it's hard. Everything is online. It's hard for Google, even for Google, to make it different. Very curious. So how is the modeling network in Belgium with Europe? Did you get more connected during?
Yeah, I would say there are three groups that works on a network, in general dynamics on networks, here in Namur. Then there is a group in Louvain-la-Neuve, which is 30 kilometers apart. And then there is a group in the northern part in Ghent, so in the Flemish part. And we and the guys in Louvain-la-Neuve, we are more on a theoretical approach on networks, while in Ghent, they are more applied in particular to epidemics. And in the last COVID crisis, they worked with the federal office to perform the line guides and so on to follow.
And how was the modeling with respect to reality? Did they?
So these guys use the model that one can call starting from a microscopic approach. So they really simulate 11 million of persons, so the inhabitants of Belgium, more or less take into account all the possible exchange they have. So the frequency that so children meet, or the frequency at which elder person meet young, and so on. So it's not really a model; it's a simulation.
Mm-hmm.
And so on this simulation, they perform several scenarios, and they say, okay, if you stop, I don't know, 50% of interaction, then you slow down or not.
So it's empirical modeling.
Yes, strong empirical, really based on simulation. So they have a lot of parameters. Yeah, I don't know how I can measure all these parameters, but also I cannot say how the system depends on each parameter, because they perform each parameter change independently from the other, but there are of course non-linearities. So I would not say that I'm not confident with the model, but I'm not confident with the long time predictions.
Mm-hmm.
So 1 week, 2 weeks maybe, but more than this, no, I think it's not possible.
Yes. Okay, so I think we can. I will activate. Now we are in streaming, but we'll activate the record. That then we'll put that in the main page. And it will be good, Timoteo, if briefly you mention to the student your path, because this is good for the student to know how people get. Okay? So, okay, I'll record. So, good morning, bon dia. Today we have the pleasure to have Timoteo Carletti from Europe, from Namur. Actually, is Bruxelles maybe, or is Namur, is home or office. Anyway, it's from Belgium, and Timoteo is a very talented and interdisciplinary person. He started in dynamical system, we can say, but then he got more and more curious about application in other fields, in many more interesting fields. So he's a hub. We can say he's a hub of connecting many other nodes. And he got interested since sometimes in complex networks with a very diversified application. And it's been a pleasure to invite Timoteo in different parts of the world to give this his mini course. Last time was in France, and today is in Brazil, in Rio, even in this remote. And so please, Timoteo,
Okay.
thank you very much.
Thank you, Stefanella. Thank you for the invitation. I'm glad the next time we will be in Rio for real, not just by distance. So I hope you hear me because I have not my macro, but if you want, I can put it. So I'm in Belgium, but I'm from Italy, and I studied physics in Florence, University of Florence. Then once I graduated in physics, I moved to a PhD in mathematics, half in Florence and half in Paris is where I met Stefanella indeed, in the Bureau de Longitude or Institute of Celestial Mechanics. And then from this PhD, then I moved some postdocs, always in Italy, Europe, so in France also. And then I end up in Belgium as a professor of mathematics in 2005. And now, since then, I'm here, I'm professor of mathematics. We are in applied department of mathematics. And so we prove theorems, but also we are interested in using real data to model, to predict several real phenomena. So I would say that I'm more a theoretical one from a theoretical point of view, but I'm really interested in application and real application. And so today I will present some results about epidemiology. And the idea is to go from the mean field, so the average model, to the network one, so the precise where you have all the agents. And I saw that you already had some previous lecture on epidemics and network models, also both. So maybe sometimes I will repeat something that you already saw yesterday or maybe some week before. So please, if it's too easy for you, just tell me and I will go on faster. Otherwise, I just repeat to better fix the notation. Also, I can only see few persons on the slide. So if you have any question, do not hesitate to ask the question during the talk because it's a lecture, it's not a talk. So if you want to understand, please interrupt me and then I can try to better explain my ideas. So this was the first title, but then I saw the last three talks that you had, and so I put an extra. Okay, it doesn't work. Okay, so I put an extra word and beyond. So I will present you some very recent result where epidemics can be studied beyond the network model. So this is really papers published last year or even in this year. So really recent one. So from the title, so epidemiology and then mean field network model. So epidemiology or epidemics is, of course, the study of infectious disease in humans, but also it can be virus in computers, so it can be informatics. It can be also spreading of news, fake news, fashions, and so on. So I think a very good starting point is this book. Is two authors, Anderson and May, and it is a very good one. So if you're interested, you can start here. I think epidemics is very complex domain. Complex, not in the sense in complicated, but really complex in the sense of complex systems. It's a science that mixes together several aspects of a phenomenon, and you cannot cut the problem in parts because once you cut, then the phenomenon disappears. So you cannot study epidemiology without considering the whole. Epidemics is complex because, first of all, the virus is complex. We don't know exactly how the virus works, how the virus spread, which is the parameters of the virus. Secondly, I think even more importantly, we human, we have a complex behavior because we human are, in some sense, the vector of the infection. So I get infected because I meet someone that already got the infection. So the virus is the reason, but we are the vectors. And so I will say that while an infection is a natural phenomenon, an epidemic is more a social or social-political phenomenon. So you have to take into account how people interact, how people move, how people go around in a country or in the city. So the second part is the network. So I think that everybody knows what a network is. Here I put just 2 books, but there are a lot of books. The first one is the one, the black one is Networks by Barabashi. Is one of the most famous researchers in this field. I think can be one of the father of the pioneer of network science. Started, I think this year is the 20th anniversary birthday of this network science. The second one is Vega Redondo. It's a complex social networks. It's more analysis of networks in the social context, but you already had some talks about, so this is a very large domain. And
What's
then
the name?
in the middle, you have the two. You have this kind of research groups where you use the epidemiology and the network model to understand how epidemics spread at the level of the world. So this Glimwitz website, I can try to, okay, can you see me? I'm still sharing my screen or not? Did you see
It appears blank.
Blank, sorry. Okay, I cannot share. So I will send you my slide, and if you click on this slide on the middle, you will access to this Glimwitz website. This is a global pandemic.
Usually, if you share the whole desktop, should do it.
Yeah, but then I have to, yes, I have to stop share, and so I start again to share.
Share the whole desktop.
Yeah. Okay, and now let me look. Okay, so this is the website that I'm talking, and here, so this, as they say, is the global simulator of these epidemics. They take into account, of course, the kind of virus, but also how people move across the continent of the countries, take into account of flights, take into account local mobility rules, and so on. So this is really a huge simulator with a lot of parameters, but then they can predict at few weeks, say 1, 2, 3 weeks, the behavior of an epidemics or a pandemic. So if you want to have a look at this website, there is a simulator that you can download, that you can play with if you want. So it's really open source. So then let me look again for my, okay. Okay, so this was from the epidemics. And then I just quote, I think you already had this quotation during one of the previous talk, so that all models are wrong, but some are useful. So the point is that here models is a representation of reality. So of course, being a representation is not the reality. So of course it's wrong. But then it depends from the question you're interested in. You can have good models or less good models, because really it depends on what you would like to tackle as a problem. A model is, I don't know, maybe you are too young, but once you have a map on a paper sheet map of some country, and you want to move from point A to point B, this map is a model of the reality. But of course, there are some finite amount of information in the map. If you want just to go from city A to city B, a highway map can be enough. But if you want more information, the map is not enough. So you have to improve the map. This is what Google Maps do, just improving each time the application. Okay, so you will see several models in my talk, and so I will not say this is the best model or the worst model, but there are several models, each one which is good for something, so to try to answer some question. Okay, so I divide my talk in 4 parts. So I studied the first part, epidemic models. There are things that you already saw previously. So here again is a website. I'm trying to, again, so it works. So this website is called Epidemics. The idea is that you can play with this Java applet. Here you have a population, where you have a susceptible person, the white one, and then few infected. So let me remove the immunity. And then you just play with the transmission rate or the recovery rate, and then you say play, and then you see how the infection spread in the network. And then at the end, you have a few, okay, so I didn't completely remove the immunity, so people can recover, but I don't want they can recover. And so at the end, you have a population which is divided in two groups, and so on. But then you can divide the population, for instance, in two subgroups, and then you can play again. So let me start again. And then you see that a person moving from block to the other. So this mimics the movement of person from, say, one city to another. And then you can play at least with 4 groups and so on. So this is a simple simulator where you can play with the transmission rate, recovery rate, migration rate. Of course, if you remove migration, they cannot move any longer, but then you can increase migration. And you see that the migration has an impact on the epidemic spreading. Okay, so this was just to show you some like video game. And so I think this is the first starting point, this Kerr-McKendrick model, almost 1 century ago in 1927. This is the standard model used in epidemics, where you divide your population in classes, and you think that each class, all individuals in the same class behave in the same way. So here is an example with class M, S, E, I, and R. And the idea is that, as I said, there is no space, there's only number of persons belonging to each class. And then you can move from one class to the other according to some rate or some probability of some event to arise or not. So the simplest example is the SIS. So you are a person that do not have the virus, but they are susceptible to get the virus. Then they can get infected. Say every time they meet someone which is infected with some rate A, they become infected, but then they can come back, so they can recover from the infection, but being again susceptible. This is like the common flu that each year, more or less, go around the world. And if you get the flu this year, it doesn't prevent you to get it next year, because there's some small changes that you are covered with respect to the flu of, say, 19, but not for the 20, and so on. So this is the back and forth model where you go from S to I and then back to S, and so on and so on. And so here, if you call S the number of susceptible and I the number of infected, you can write down a simple model. There are differential equations because I do not consider space here. And so you have the time evolution of susceptible person is proportional to the number of infected, because as say each time infected produce a susceptible one, but each time infected meet a susceptible one, with probability A, the person becomes infected one. So you pass from the group S to the group I, and then back inside. So I had some very fast simulation. I use MATLAB, but you can do whichever you want. So here I just integrate the model that I just showed you by fixing 2 parameters. A is 1.2 and B is 1. And if you do the simulation, you see 2 curves. The blue one, which is the curve of the susceptible person, and the red one of the infected one. So I start from a normal case where we have a very large number of susceptible, so normalized to the total number 1, and you have a very few number of infected. Then you have the infection that rises, but then it's stabilized to some number, is more or less 20%. So in this case, it means that at equilibrium, you have 20% of persons that are always infected. So it's not the same person that is infected, because each infection switches back and forth from susceptible to infect, but the number is almost constant. But then if you change a bit the parameter, I don't know, I can go to a bit less than 1. You do the same. Then in this case, you don't see anything, because indeed, if I make a zoom, you can see that the number infected started, but almost immediately goes to 0. So this is what you saw in the previous talk called critical or subcritical epidemics. And to understand this criticality, okay, so this I already saw this. So to understand this criticality, you have to introduce this basic reproduction number, R0, which is roughly say if the epidemics start propagating, so at the beginning is exponential, or if the epidemics goes to 0. And this is very easy in this model because if you take the derivative of I at time 0 or at the beginning of the epidemics, then you can approximate, so you take the second equation, then you can approximate the total population as 0 by 1, because I normalized to 1. And then you can just put I of 0 and B out of the parentheses, that you end up with A over B minus 1. And then the derivative of I at time 0 is positive if only if A over B is larger than 1. And so this A over B is what is called R naught, so the basic reproduction number that you can hear of in all newspaper, journals, so on. You want this R0 to be less than 1. So in this very simple case, it's clear why. Because if R0 is larger than 1, then you have the increasing of number of and then they stabilize to a fixed number of the population. Okay, so this is a very simple. In more complicated example, it's not so straightforward to compute R0. Okay, so the second step is to introduce this SIR model, where once you have susceptible, you get infected, and once you recover, you can never get back to the susceptible case. So this is the case of COVID. We think that once you have COVID and then you healed from COVID, then you can never get the infection again. This is what is believed, but it's not so clear. But this is the case where you cannot get twice the same illness. So here again, I have a small a, which is the infection rate, where susceptible people meeting infected ones get infected. B this time is the rate at which infected people get removed, so it can be dead or immune to the virus. What is important is that cannot any longer diffuse the illness. So in some sense, having a large number of our population is good because they cannot spread any longer the virus. Okay. Okay. So again, here, if you write the model, you end up again with a differential equation, so a system differential equation, because I do not consider space again. And now the first equation is as before, because you say that the number of susceptible persons decrease as a product of number of susceptible times number of infected. The infected increase by the same amount, but decrease because with a rate B, the infected becomes recovered. So here, if I do the same simulation as before, now again, I fix some parameters. So I start again with a 0 recovered, because at the beginning of the population, nobody has already recovered yet. There are very few infected. And then I put some parameters for the simulation, and you will see the standard curves that you see. Let me just make a zoom. The initial part, you have the blue curve is the curve of susceptible. So you start from the full population to be susceptible, but then they goes down, they almost disappear. The red curves is this ghost or this bell curve that everybody heard also in the mass media. You have to flatten the curve. This means this is the peak of the infected. You want this peak to be as low as possible, because otherwise the hospital cannot handle everybody. And the black one is the number of recoveries, so the person that cannot any longer transmit the infection. Of course, it is just a game, because I put the parameter at random, but playing on the parameter will tend to lower or push higher this red curve. So this can be a problem in a real scenario. So let me back to the okay. But then, so you can modify this simple model in many ways. You can add, for instance, vaccination. Vaccination means that the susceptible person can pass directly in the recovery case, because they cannot any longer transmit the disease without being infected, so we don't pass it to the hospital. This is a possibility. Then you can also consider that the virus mutate, and then you can have several strands of virus that in some sense compete for a susceptible person. This is also something that is now studied for the COVID, because apparently the initial virus from China has mutated once it gets into Europe. And so you can, once person go to the hospital and they get some tests, then the doctors can measure, or sometimes they can access to the DNA of the virus and to understand from which strains it comes from, so to understand from where the person has been infected. You can add a time delay, because you need some time to the person once you are infected to become really able to spread infection. This can be done using a fourth compartment called E, so the exposed but not yet infected, or you can just add a delay in the infection. So the probability, so the derivative of infected now is a function of infected sometimes before, say 1 week before or 1 day before. In this model, I consider that S is fixed in the sense that you can only become from S infected or recovered. But in principle, if the infection lasts a long time, then there are newborns that are present. And so you can consider natural birth and death in the model. So you can open the model. Of course, then you should make some assumption. If a newborn born from a mother that is infected, should be the baby infected or not? So that all kind of hypotheses that you have to do to model your virus. Of course, you can consider age groups, which is very important, because we saw in the COVID case that the impact of the COVID on the person strongly depend to the ages. The most dangerous is, so from infection related to death, is for persons that are 70 and more, while so this means that the rate that I consider are not constant through the population, but depends on the class of age of the person. So these are all possibilities that you can take into account. Okay, so now before to go to the second part, I would like to introduce this SIRD model to show you that indeed this model, even if they are very simple, they can in some sense predict or can be used to predict the COVID spreading. So my point of view is that, okay, complex models are useful if you want to ask a very fine question. But sometimes simple model, as the one that I'm showing you now, so with few differential equation, a few parameters, can also be good to provide some answer. So the SIRD model is like the previous one, where I differentiate now the recovery from the death. So there are persons that from the class I, so defined infected, goes as before to the R, so they recovered, so they cannot any longer spread the virus, but there are also a class of persons that from infect, they die, so they cannot spread the virus, but they die, so they are no longer there. So this is something that you want to minimize in a real case, okay? And so the point is that you can write this model. Now he has 4 equations, because it's the rate evolution of number of susceptible, infected person, recovered, and death. But then you can observe that if you make some analysis of this model, first of all, the total population is constant. Indeed, if you add the 4 equations, so the total population is the sum of the persons that are in class S, I, R, or D, you can observe that the derivative of n is 0. So n is a constant. Then you can play with the third and the fourth, so the one for R and for D, and you can realize that the number of recovered cannot be independent from the number of death. They are related by this linear relation, the second equation on the left. And so the number of the recovered at some time t is a function of the number of initial recovered, so 0 if you want, but then it's proportional, directly proportional to the number of death. The same thing you can play with the first and the fourth equation. You can see also that the number of susceptible person is not independent from the number of dead person. They actually are this exponential linking between them. So you have 4 equations with 4 quantities, but you have 3 constraints. So actually you can reduce the dimension of the problem to just one differential equation. Indeed, you can write an equation for d dot equal some function which depends only on d and on the parameters that are the parameters that appear in the original model. So this is a really simple in some sense model because you have one differential equation, something that a student of first or second year mathematics should be able to solve. And on the left, I show you the curve, which is on the horizontal axis is the number of deaths, so D, and on the vertical one is D dot. This is the graph of the function f. So I fix some parameter p, and I plot this function. And so the question is, does this simple model can be able to describe the data for COVID? But what you can do, you take the total number of deaths that you can find on any newspaper and so on. You put on the vertical axis the number of deaths per day, which is also information that you have, and you put on the same plane. If the data collapse more or less on the curves, good, you're right, or otherwise not. Okay, so as can you expect, the data fit very well. So this is the case of Belgium, where the dots are the real data for the death and the death per day for the first 2-3 months of the epidemics in Belgium, and then the curves for the previous curves. And so you can see that, of course, there are fluctuations because these are real data, this is a real scenario, it's not just my toy model, but you can see that the agreement is quite good. And also the R naught, which is this famous parameter that should be more than 1. This was at the beginning of the epidemics, so it's 4. Maybe it's too large, but it's reasonable. It's not 0.1 nor 10, so it's something which is reasonable. What we did, this is a result that I got recently with some colleague of mine. We did the same for a lot of countries in the world. Unfortunately, I don't have Brazil because this has been done on the 1st of June. And that moment, we didn't get enough data for Brazil. But you can see that almost all countries, I think they are almost from Europe except the last line, they almost all fit with this curve. So this means that in some sense, this simple model SIRD is able to capture the behavior in some sense of the epidemics at this scale, at the scale of a country. So I cannot see in which city of Italy there will be a lot of death or not, but at the level of all the Italy, the agreement is very good, for instance. So I think this is a proof in some sense that you can also use a simple model to understand complex behavior. Of course, there are these variations. I think now it's interesting to understand why these variations are there, and if you can understand why, for instance, Sweden is so scattered around this curve. We know that Sweden gets a different approach with respect to lockdown, not to lockdown. So maybe this is the reason. So Austria again. So we did analyze this behavior, but it can be done if you're interested. So if you're interested, this is the paper that I'm talking about. It appeared a few months ago in this journal, Chaos, Written and Fractals, where we study exactly how these simple models are effective to understand this complex behavior. So in the paper, there are more details. There are also other analyses. So if you're interested, I can send you the paper, or you can find, it's open access, so you can find it without any problem. Okay, so if there are no questions about this first part, I can pass to the second part.
One question.
Yeah.
The model, the daily, because what we observe in Brazil, that we have a delay in the reports of the death, because actually even something that was passed at the end of, not a law, but a sort of law that was passed at the end of March. So people didn't have obligation to report immediately to the register office the death. They had 2 months period. So we observe more or less 1-2 weeks delay at least. So this curve, did you do this daily death per day? Did you try to average with windows, taking account the possible?
Okay, so let me start. So why do we choose to use these variables, so death and death per day? Because at least here in Europe, at the beginning, the number of infected, it was not reliable, because they perform tests only to persons that are for sure get the virus and go to the hospital. And so this is an underestimate number of real infected. So if I had used the number of infected reported every day, I would not get the good parameters. While, at least I repeat, here in Europe, it seems that at the beginning, the number of death was the good count of death. Of course, there are some problems. For instance, on the weekend, they do not report the death number. And so on Monday, we have more death and so. So for the reason, you can do a 1 week average with a moving average. So we can, in some sense, smooth the data. But we really think that the number of death is more reliable than the number of infected or the number of recovered also, because if you get the infection and you stay at home, you never go to the hospital, you never get a test, you are recovered, but nobody knows. So you are not in the daily count. So I think that the infected and recovered is not good. Now, number of persons in the hospital is good because they really count, but then you have to modify the model because you have to take into account which is the fraction of infected in the population that go in reality to the hospital. And we don't know. At the beginning, maybe it was maybe person or elder person, now are more young person. So to avoid this compromise between using infected, hospitalized person and recovered, we use daily death, but average over 1 week. In some sense, we can remove this spurious number from weekend mostly.
Okay, so you did average over 1 week.
Yeah, over 1 week. Because if you plot the curve day versus number
it's
of
too
days,
it's too
there are a
noisy.
lot of spikes. They correspond to weekend. They correspond to holidays and so on. You cannot make a model take into account there is a weekend because the virus do not know there is a weekend. So they
we in Rio we have in the state of Rio we have these curves. We have this curve for all the municipalities and even some part of Rio. So it would be interesting to see.
Yeah. But I think these curves are very easy to be done.
No, we did. We already did it, and we were doing this averaging and so on, 1 week averaging. But then, in our case, maybe it was 2 weeks that at least sometime at a certain point it became 2 weeks. It always seems that the curve was decreasing, but then if you wait enough, then you went backward, you see that it was increasing. So we had this kind of.
If you want to trust this model, and then you put your data and the data do not fit too much well on the curve, you can say there is something which is missing. This can be the 2 weeks late of data, for instance. Or you can see, okay, we applied a good lockdown, so the lockdown is not written in the model. So if the data strongly disagree with the model, maybe it is because there is something we are not considering, the lockdown, for instance. So you can use this model to check the reality if you want. Okay, good. Okay, so if there are no more questions, I go to the next part, so network models. So here again, you got some lectures, so I will just present some basic introduction about network models, but feel free to ask question or something more. So networks are everywhere. So what is a network? A network is a very general framework where you can model a lot of phenomena, because a network, what is at the end, you have nodes that represent basic units. Units can be person, can be your computer, if you think of computer networks, can be protein, can be power plants. And then you say that two nodes are connected if they interact. The interaction can be anything. In the case of gene or proteins, it can be an interaction between proteins. If you have an interaction among persons, there can be social interaction, friendship. The plot in the middle is social patterns. Each dot is a student in the school, and each color is a class. You can see there are a lot of links between students of the same colors because the interaction inside the classes, but you can see there are links among groups, and there are interaction, maybe they are doing the playground, or maybe are friends and so on. So you can really understand what happened in your model just looking at the network. Or you have the social network that everybody knows about, Facebook, Twitter, and so on, where the nodes is your account and the link is the friendship, or I follow you or reply you. Or there are networks where are really wired in the sense of the link are really cable. In the case of power plants, a link is really a cable transmitting energy from one power plant to the second one. Or you have these world flight maps where nodes are airport and links are connection between two airports. So this is a very generic framework for the reason is everywhere, because you can model almost everything just by interacting unit in some sense. Just to fix some notation, so at the end you have nodes that I call with numbers 1, 2, 3, 4, and so on. You have links that connect to nodes, and I call links with E for edge, because they are also called edges. In some cases, you want to preserve the directionality, because you know there is some cause from going from 1 to 2. It's not the same for going from 2 to 1. And so in this sense, you speak about of directed network or undirected if you go in both directions without any problem. It's very useful to use to encode your network, use what is called adjacency matrix. It's just a matrix where the index I and j are the nodes, and this matrix is equal to 1 if node I and j are connected, at zeros otherwise. So if the network is symmetric, so if it's undirected, so the link from 1, 2 is equal to link to 1, then the matrix is symmetric, otherwise it's not symmetric, it's antisymmetric. And then you can speak about the degrees. The degrees, if you think of Facebook, is the number of your friends. In the network is the number of nodes connected to the given node. So the degree of node 1 is 3, because there are 3 nodes connected to him. So the nodes 2, 4, and 3. The node 5 have degree 0 because he's alone, he's isolated. There are no friends for him. Okay, what one usually do once he has a network is to study the degree distribution, say, which is the fraction of nodes that have degrees 1, 2, 3, 4, and so on. This shape of distribution can tell you something about the structure of the network. So you have heard about a complex network. A complex network means that you have a network whose degree distribution is not trivial. You can say it's not constant, like a lattice. A lattice, every node is connected to 4, so north, south, west, and east. If you have a 4 lattice, you can have an hexagonal lattice with 6 neighbors and so on, but its number is a constant. Or you have what is called a random or Erdős-Rényi network, which is Poissonian. So each node is connected on average with the same number of nodes of everybody. So there's sometimes the simple one. If they're not simple, we say it's complex. Complex, now I will show you some example of complex connection. So in the case of Erdős model, as I told you, I think you already saw this example in the previous talk. Then that is that you give n nodes, and then you check for all possible couple I and j if there is a link or not. And this is given some probability p, which is fixed once for all. And then this is a binomial distribution after all. And so you can compute the probability that a given node has some degree k, which is the formula down there. And then you can compute the average degree, which is just n times p. Being n a p constant, the average degree gives you the idea of how many friends or neighborhoods each node are, and this is the constant. And this is a good representation of the networks. In fact, that if you take node 1 or node 10, locally they look the same. They look as having n times p friends or neighborhood each one. A second model, which in some sense interpolate from the lattice to this Erdős-Rényi, so random graph, is the model called Watts-Strogatz, by the names of Watts-Strogatz, the two researchers that proposed this model in 1998. I first show you the model, then I explain the reason behind. So the idea is the following. You start with the regular one, is on the left. Here, each node is connected to is 4 neighborhoods. If you look carefully, each node are 4 links related to him. Then you have a parameter p. With probability p, you flip all the links. So you take the links 1, 2. With probability p, you remove the links from 1 to 2, and you put from 1 to anything else, and so on. You do this for all the possible nodes. Once you have done this, you have a new network. If you now move p, if you go to the extreme case when p is equal 1, actually you have reshuffle completely your network, you end up with a random network, okay? But in the middle, there is a regime of values of p that depends actually on the number of nodes where some interesting emerging phenomenon appear, which is the phenomenon called small world. So the reason for this model is the following. There has been an experiment in the US in 1960, the Milgram experiment, which is a sociologist who sent a lot of letters in paper letters to person, but say, okay, you have to send this letter to this guy that you don't know, but you have to send to a friend of you that should send to a friend, to a friend, to a friend, up when this letter will reach the person that I choose at the beginning. Okay, so I repeat, you give me a letter, I have to send a letter to one of you. I don't know you directly, but at least I sent to Stefanella because for sure Stefanella knows you directly, so she will be able to send you. But then if I want to send a letter from maybe someone else, I don't know, someone who lives in Argentina, maybe send to Stefanella, will send someone in Brazil, then someone living in Argentina because of research and so on. But this is the idea. So the question was, how many steps does each letter to perform from going to person A to person B? If you take into account that in the US, there were at least 150 million, 200 million persons at the time, one thinks a lot, because if you start, say, from Los Angeles, you want to go on the other coast, on the middle, you say, a lot of steps to do. The result was only 6 on average, so between 5 and 6. So in only 5 steps, you can send your letter to someone that you really don't know it exists before. And so in some sense, it's astonishing. You can, now this game has been repeated in very different situations. You can say, if you can measure the distance from you from having, I don't know, from someone that knows, I don't know, a Nobel Prize. Okay, it can be enormous. It's not so large because I know the rector of my university who for sure knows some prime minister in Belgium or even the king of Belgium, which for sure knows the king of Sweden, that for sure knows someone that has a Nobel laureate. So again, it's a very short one. So this idea that in a network with a large number of nodes, you still have a very short cut is really important, as is captured by this model introduced by Watts and Strogatz, and they show that in this intermediate range of parameters P, you have this small world. Small world means that if you compute the average distance between all the couples of nodes, this distance is very small. And this is important if you think of spreading of epidemics, because, okay, I don't want to spread the virus, but if I meet someone, in only 6 steps, I reach someone which is very far from me, but this means that the virus can spread very fast. So in some sense, if you want to prevent the virus from spreading, you have to increase the length of your network and not to reduce. If instead you want to I don't know, spread information about good news or a picture, then you want to reduce the dimension of the net because you want that your picture is seen by everybody in a short time post. Okay, so this is the idea of this network. In this paper, you can find, or I can send you, there is an analysis of the length of the average path as a function of this parameter P, and you can study in the both limits what happens. Okay. Then okay, so I didn't remember there was there is a range of parameter where the length that I call L is small, while the network is still has still a large clustering coefficient, because of course if the clustering coefficient measure how many triangles there are in some sense, which is the probability that 2 friends of mine are also friends among them. In social sciences, this is very high. Normally, in a normal network, we don't know. So the clustering coefficient is a measure of this, the probability that 2 linked nodes to the third one are also linked together. And so, of course, if everybody is linked with everybody, the path is short, but also the network is very collapsed, is a blob. And so the clustering is very small. So this small world phenomenon is interesting when you have low path, but high clustering, in the sense that there is no so much blob effect in some sense. Okay, the last model is this the Barabashi-Albert model, also called the preferential attachment. So here the idea is really inspired by sociology. Assume you arrive in Belgium, you want to meet someone, so you are a Erasmus student, you want to meet someone, and you cannot try to make a friendship with someone and take a random, but maybe you choose someone which is in your group of Erasmus students. Maybe you choose the one that are already a large number of friends, because you say, "Ah, this is a very smart guy, I can help, I can have some help if I'm in friend with him or her." So this is the idea that once a new node or once a new person enters in the network, he tries to have a connection with already existing node, but selecting first node that have high degree, so a large number of neighbors of friends and so on. And so in this paper of 1999, Barabashi and Albert studied this process, and then they proved that once you do this, you can show that the distribution of the degrees is a very precise law that is drawn here, which is the probability to have degree k is 1 over k to the power 3. And so this is called now scale-free or broad distribution, because if you plot in a log-log scale, you have a straight line that tells you the probability to have degree k, okay, is small if k is large, but this 1 over k to the power 3 is much, much larger than in the case of Erdős-Rényi. Erdős-Rényi is more or less an exponential, and so if k is large, the exponential is almost zero. The probability to have 100 friends in an Erdős-Rényi network is almost zero. Why the probability to have 100 friends in a scale-free network is not so zero. Indeed, once you have a friendship network, there are a lot of persons that only have 1 or 2 friends, but there are some persons that really have a huge number of friends. So this kind of preferential attachment network really describe what happened in real society. But indeed, in this paper, they study also internet or the www, and they show you that this is the same in this case. So there are routers or main access point that are connected to many, many other routers, but there are a lot, so there are few one of them, but there is a large number of routers that just connect to one computer or two. So they are really important feature. Now this kind of model has been modified in time, and now you can have this scale freeness not just with this exponent 3, but with any gamma. Gamma should be larger than 1, because if gamma is smaller than 1, then the average degree is not defined. And so if you do a simulation, you can end up with very, very large average degrees. And if gamma is between 1 and 2, the average degree is defined, but not its variation. So it's standard deviation. So if you do several simulations of this network, you have an average degree which is fixed, but it can fluctuate a lot because of the variation. While if gamma is larger than 2, then both the average degrees and the standard deviation are fixed, so they're small numbers also, so you can compute easily in some robust way this network. Okay, so this is the third model that I like to introduce. And so now, if you are okay, I can go on and mix these two parts, epidemics and network, to see what happens. Just look, I don't know, tell me if I have to stop with the break. Is that as you want?
Yeah, we can have a 5 minutes break, 10 minutes break. It's good for people.
Oh, okay.
Yeah, I think it's good if we have 5 10
Okay.
minutes.
Good.
Okay.
Okay, good.
Okay. Very good. Very good. I think Brazil is a challenging network. we are very highly mixing, but at the same time, it's very highly fragmented. So it's
Yeah, in Belgium, there is a professor that I told you before in Ghent. He's Luis Rocha. He's from Brazil. And he studied a lot of networks in Brazil. I think one was a network of prostitution in Brazil. And to understand how illness can spread among partners and so on.
Yeah, because for example, at a certain point they were doing about COVID, the percentage of people infected that were dying, and we had that in the favela. We had in one of the favela where they had more data, because also this is the difficulty. We don't have, people don't go to doctors in the community, so we try to think about telemedicine more than, you know, to try to reach out at least first aid. And so we had the favela of Maré. There was a very, I mean, I don't know how to describe this data, but they were that among the infected, 30% were dying. It was like huge. But of course, you know, who knows, maybe there were many more infected, as you say, you know, this percentage of the one day, you know, they were infected. And people do not go to the hospital.
Because
you know.
there are infected that are asymptomatic, so maybe if they don't go,
exactly.
no problem. But there are infected that are not asymptomatic, they are symptoms, but they do not go to the hospital. This is dangerous.
Yeah. We have this, and we have that now. We so in this, already in March, we had, for example, in Amazonia, we had that they were circulating H1N1, and together with COVID, and together with tuberculosis. And here in Rio, tuberculosis is endemic. So we had, I know people that, you know, in some of the community, they had first COVID in March, and in May or June, they got tuberculosis, the same family, you know. And then it's huge. If one gets, everyone gets, you know, because people visit each other, you know, especially if you confine them even more. So we have these multiple things. and the public network of hospital is not done to attend all this, but also the private were in crisis, you know, because people, if you ask the doctor, goes, do not come, even if you have. So we had both systems that were kind of, and the doctors were getting sick, and the nurses were getting sick and die. So we had, at least in Rio, a lot of doctors and nurses that they were getting infected, and a large population, I think it was 70% or something like this, a huge died, I mean, like a huge percentage of death, because the test didn't get to the population until lately, you know, now they're testing, but, you know, for months. And and people in some of the public hospitals, they didn't have all the equipment like you see in China, you know, to work in the most safe conditions. So we have this kind of problem. But okay, so let's make 5 minutes break.
There is someone in a waiting room. I think you have to admit.
I didn't see. 1 second. So, isn't there a waiting? No, there is no one in the waiting room.
No, I saw in my screen Gabi Basilio entered the waiting room.
Yes, no, but we have Jose that is taking care.
Okay.
Yeah, she's already, I think internet went off. Okay, so 5 minutes break.
Yeah,
okay. Okay. Allora, possiamo, we can start again. Please.
Okay,
Timoteo.
so welcome back. So now let me start this third part, which is merging together the first two, so epidemics and networks. So once you think of a network, as I said before, you can think that one node is one person, so which is called social networks. And the links are so the connection between person. So in this case, so let me start again with the first model, the SIS. So I remember here on the left, you have S is the number of susceptible person in your population. I is number of infected, and then you can get the virus with probability A. But then with probability B, you can, in some sense, recover and become again susceptible, and so on and so forth. So this is the initial model with no space. And now if I say that each node is a person, then I can consider a first approximation where S, okay, of course, because the total population is preserved, so the S plus I is equal to 1 over N if you normalize, if you don't normalize, then you can start considering that any nodes has the same number of neighborhoods. And so the probability, if you want, that a susceptible person meet an infected one now should be weighted by the number of friends that they have, or the neighborhoods. And so if I assume for the moment that they almost have all the same number of neighbors, then I can just replace A by A times the average number of degrees. And then I replace S by 1 minus A. And now you have two time scales, that the time scale which is A times the average degree, so something depending on the network topology, and then B, which is the time scale of the virus. If you consider now again what happens for short times, and you do this as before, you linearize, you assume so the I is small and the S is almost 1, then you find that the derivative of I is proportional to this A times K minus B times 1. And so now you can see that the derivative is positive if A times K divided by B is larger than 1, or is negative, is smaller. And so this is now the new epidemic threshold R naught, which depends not only on A and B, which are the parameters of the virus, but also on the topology of the network. So the same epidemics on two different networks can spread or not according to the degrees distribution. Okay, you can also compute the total number of infected person equilibrium. If you remember my first simulation, the red curve started at 0, then it grows, and then stabilizes at some point. Then this is what is called I infinity, so the asymptotic number of infected person. Then you can plug this information in the previous equation, and then you end up with a nonlinear equation that can be solved for I infinity. And again, the solution depends on the product of A and B, which are the various parameters, but also on the average degree. And you can see that if A times average K divided by B is larger than 1, then you will end up with an endemic infection, because there is a constant fixed number of infected person, while if the A times average K divided by B is more than 1, that at the end the epidemics goes to 0. So there will be only susceptible person. So again, here is important fact that the fate of the population depends also on the topology of the network, on the social net, not only on the virus properties. Okay, so this is can be put in a single picture, which is this one, where this is what is called a phase transition. So if lambda, which is the virus parameter, because it's A divided by B, is smaller than some lambda critical, which is 1 over K, then I infinity is 0. While if you pass this average, this critical value, then you have a finite positive number of infected person population. So this is really an important parameter, because if we think that your epidemics is dictated by this SIS model, which is not the case for the COVID, but can be for other epidemics, then what you have to do is to modify your network in such a way the average degree is large enough to be beyond the threshold. In such a way, you can prevent from the epidemic from spreading and so going to zero. So this is a way to control, if you want, the epidemic. Okay. Now let me pass. So I started this part by assuming that almost all nodes have the same number of friends. So that's why I can use the average degrees as a single number. But in reality, so in a network, in a given network, each node has a different number of friends, so different degrees. But then I can make the following assumption. So I assume that all the persons that are in the same class, so all the susceptible that have also the same number of neighborhoods, they all behave in the same way. In the same way, all the persons that have the same number of all the infected persons that have the same number of neighborhoods, they also behave in the same way. So in this way, I can create a new classes, which I call class X, where X can be S, I, or R, it depends on the model you want. A K is the index of the degrees. So I have as many classes as the degrees of my network. So it can be huge, but it's still a good approximation. It's an approximation because it's lower than the number of persons in the network. It can be millions, while the degrees are not so large in principle. Okay? And so with the small xk, I denoted the fraction, and then when I multiply it by pk, so the probability to have degrees k, I obtain the average number of persons in the class X in my population. Okay, so if I write the previous model for, I only consider here the infected variable, so is small I because it's normalized by the total population. I remember the index k is the number of neighborhoods. So how can the number of infected increase? But there is the parameter A, which is the strength of the virus. K, because it's the number of friends that this infected person that meet. 1 minus ik is the number of susceptible because it's a constant, as I said before. And theta k, so this strange letter, is the, as I wrote here, is the probability that a link from a person with k neighborhood is linked to a person with k prime neighborhood. So it's the conditional probability of having degree k prime, knowing that my friends has degree k. So this equation so tells you that the number of infected persons with k friends can increase because there are persons with k prime friends whose friends have k friends, and so one of these k friends can be one that's in contact with me. Okay, so this is the short of this equation. And the last term minus bik is just the natural way where infected can become again a susceptible person. Okay, so in this new equation, now there is this new probability, which is the conditional probability, the pk prime k, which is difficult to compute. So what can do is the following: is one can assume that okay, so before this extra hypothesis. So now you can study. So maybe instead of studying this equation for ik, I can multiply this equation by pk prime k, and so studying the same evolution for the variable theta k, not for each variable ik. If you do this, you end up with this equation where now you have the time evolution of theta k is a function that depends on theta k prime, but also on ik prime. So I have to, in some sense, remove this ik prime because otherwise I cannot handle this equation with two variables. One way to do is suppose that at the beginning of the epidemics, again, the number of infected is small, and so the product I times theta is small, and so I can forget the first terms. In this way, you end up with the last equation on the bottom right, which is an equation involving only theta computed for k prime ak. But now the only point that it remains to deal with is this the conditional probability pk prime k. So we have to, some sense, study this probability. And so the simplest way is to assume that there are no correlation. So the fact that I have degree k is not correlated with the number of friends that one of my friends has. This is not always the case. In some cases, you can have what is called associative network, where a person with a lot of friends is usually connected to a person that also has a lot of friends. These are called associative. In some other cases, you have what is called not associative, where you have a person with a lot of friends, which is connected to person with very few friends. So one of two. Okay. So I will not consider this case, which is it can be done in the book that I showed you in the beginning, the one red and black, Vega Redondo. There is the analysis for the general case. Here I will restrict to this uncorrelated. There is no correlation from my degrees with the degrees of my friends. And this way, you can write the conditional just as the product of the two normalized by the average degrees. And so if you put this in the equation, then you lose completely the dependence on the k, because everything that remains is the average k and the average of the second momentum of k. So here again, you see that there is not only the average number of friends is important, but also the square, the average of the square is important, and again, the two parameters a and b. So I remember this is the equation that I found in the assumption that I is small. So I'm in the beginning of the epidemics. So again, I can study once this derivative is positive or negative, and this tells me if theta increases, so the number of infected persons increases or not in the population. And so if again you draw the same picture as before, you saw that the R0, so the epidemic threshold again, so A over B, now should be compared not only to the average degree, but to the average degree divided by this second momentum. And this is important because this tells that given a network, you can fix the number of friends on average you have. It depends on the number of this second momentum. And as I told you before, there is a range of parameters for the scale-free networks for gamma smaller than 2 but larger than 1, where the standard deviation is infinite. This means that second momentum also is infinite. And so this means that this k over k squared is almost 0. What does it mean? This means that for any a over b, you always have infection in this network. So if you have here, you can see this dashed line, which is the line that I showed you before in the Erdos-Renyi network, where I show you, okay, if you change your average degree to be below or above the threshold, given A over B, you can reduce to 0 the number of infected, or it can give some fixed number. In the scale-free case, because 1 over k squared can be very large, k squared can be very large, so 1 over k squared can be very small. Actually, this number is almost 0. And so for any values of A over B, you always have a finite number of infected persons in the population. Okay, but this is the SIS model, so a very simple one. But this means that if you run a SIS model on an Erdos-Renyi or on a scale-free net, which is more similar to the reality, then you will have always endemic infection in the scale-free net. So if you do something similar in the case of the COVID or SIR or SIRD, then you have a similar result. You always have a finite number of infected persons there. Okay. Okay, so here is a computation as I did before, but okay, I cannot insist much because it's difficult at distance to explain all the details. I will send you the slide, but as I show that I can compute the average number of infected persons, I can also compute the average number of this theta value, which is related to the infected by the formula on the right, in the middle right. And so this gives you the asymptotic number of infected persons having k equal 1, 2, 3, 4, and so on. Once you compute this theta infinity, okay, is an implicit function, but you can solve numerically and you can find the value. Okay, now this was the case where the network is a social network, in some sense, one node, one person. But in reality, you can have other approaches where now one node is maybe a city, or one node is a country. And so you study the epidemics as some intermediate scale between single person and the whole. So if you think that one node is a city, then you have a dynamic internal to the city where you can have some SIR model, you have some infection and so on. But then person moves from city to city, and then you have this, as I showed you in the initial animation, that you can have person that can spread the virus across cities just because they move across cities, or if you think of countries, because they take the airplane and they move from one continent to the other. So this is a new step, if you want, in the modelization. These models are called metapopulation model. Metapopulation because you make the assumption that in each node, say a city, you have enough person that they are well mixed. And so inside each node, you can have you can lose again the notion of space, and you can use a standard epidemics model like SIR and so on. And so this metapopulation has been used initially by Robert May for the epidemics, but in the case of ecology, so animals, not humans. But then now is nowadays used, for instance, in the website that I showed you at the beginning, this Glenwitz, this is the model they use to tackle the global pandemic. So they have cities that are nodes. Inside each city, they have some local rules of epidemic spreading. And then they have movement of person across cities at a small scale, like using highways, so cars and so on. A larger scale, they're using trains, and a global scale, they use airplanes. So they really do all this simulation at several scales. So the important point is that the interaction for the spreading of the infection is done inside each node, and then person spread because they move themselves across nodes. So using the edges of the links. Okay, so now you can call SI or I and so on the number of susceptible, infected, or recovered person in each city. So J is the city 1, 2, 3, and so on. And then you have, this is the model without the possibility that person move across cities. So inside is each city, but you assume that the number of susceptible decrease using, as usual, the product susceptible times infected in this city. The number of infected grows by the same amount and decay because some infected become recovered, and the recovered increase because some infected become recovered, but everybody remains in the same city. Okay, and so there are the local, if you want, variables. The variable related to the city J, a J goes from 1 to the whatever you want. Here, I assume for simplicity that the parameters are the same. Of course, you can say that some city, there are more elder persons, so the A is different, but so there are details that I can skip now, but if you want, you can introduce some heterogeneity also at the level of the parameter. And now I have to model how person move from one city to another. And this can be done using a diffusion, because after all, it's true that if I go from where I work to where I live, it's not a random process because I go where I live and where I work. But if you take a country, it's true that there are patterns that repeat, but on average, you can think that this movement is some sense random because it's not only the fact that I move from city A to city B that allows me to pass or not infected. It's also the fact that I found there someone. And so this process of moving and spreading can be considered a sort of random process. And a random process is well described by the diffusion term, where person go, if you want to visit cities more or less at random. So if I go back to the simple model of network that I presented just at the beginning, so the one with 5 nodes and 4 edges, then you can model the diffusion as following. You consider, say, node 1. You can think that the number of persons in node 1 is a sort of liquid. And this liquid can go out from the node 1, and it can go out, so decrease by this number 3 U1. So U1 is this liquid, if you want, is density. So this 3, because node 1 at 3 links, so degree 3, so it can spread along 3 directions. So the decays in U at node 1 is 3 times what is the content of U. But at the same time, it can receive the amount, so the density of the fluid from node 2, 4, and 3 because they are connected to him. Okay, so this is a local balance between what a node can spread out using the degrees, but also with respect to what a node can receive from the nodes that are linked to him. Okay, if you do this diffusion term, it is called in physics a Fick's law, which is a law that locally tends to equilibrate concentration. Then you end up by writing, if you remember that the adjacency matrix Aij is 1 if I is connected to J. Then if I take here node 1, that you can observe that U2, 3, and 4 are in just the product of the adjacency matrix times the vector U minus the degree of node 1 times U1. And so this product can be rewritten as the product of matrix A minus the diagonal matrix delta Ij, where you put on the diagonal the degrees. And this matrix that I call L is called the Laplace matrix of the network. This is the equivalent of the second derivative of the standard diffusion. So if you take the head equation for the diffusion of head, the temperature, then this is described by the second derivative of the temperature. If you do this on the network or on the lattice, then the second derivative, the Laplace operator, becomes this matrix L that I write here, which is nothing but the adjacency matrix, so which is encode who's connected with whom, minus a diagonal matrix containing all the degrees on the diagonal. Okay, so this is the way how persons spread across the network. And so if you put this with the previous model, now you have the full model that describes how the number of susceptible, affected, and recovered persons in each town, J, varies in time. If you look for the first equation, you have that the variation of the number of susceptible persons in the town J, so decrease because there is a local interaction and some infection can be done there, but then increase because of these terms, which is L times S, which is all the susceptible persons that came from the neighboring cities and stay in the cities J. Of course, some persons, susceptible person, can move from city J and go somewhere else. So this is hidden in the matrix L because it is also minus. The coefficient D is the, if you want, is the speed, is the diffusion coefficient that tells you the speed at which, or the rate at which susceptible person spread in the network. Then if you look at the second equation, the same idea. This is the reaction part. So the part only depending on node J, plus a part depending on the connection on the network. So all the topology of the network now is hidden in the LJK matrix. Okay, so you have these three coefficients, the S, the I, the L. Now you can also assume, if you want, that in reality these coefficients are not fixed and depend on the state of the system. Think of if you are a susceptible person, maybe you don't want to go where there are a lot of infection, and so maybe the coefficient D is a function of the number of infection. It is very small if infection is high, or very large if infection is small. Or if you are an infected person, you are a smart guy, you think, oh, it's better I don't move because otherwise I spread infection. So for the infected person, maybe the coefficient DI should be small. So there are also things that you can model, you can put in a model. I will not do this, but it's also things that can be done. So what I call here parameter fixed can be actually be function of the state of the system of each node. And this, of course, complexify the model. Okay, how you deal with this model? But again, once you have this kind of model, you're interested in knowing if an epidemic that starts in some node J will spread in all the network, or if you remain confined in node J, or maybe goes to zero also in this network. To do this, so you fix again one reference solution. So this is the solution of where there is no recovered and no infected. So this initial state of the system, and almost everybody is susceptible. Then you linearize the system around this equilibrium, and then you try to understand what happened, computing the spectrum of the linearized system. Here you will realize that is the Jacobian, if you want, the linear system, depends on two parts. The first part, which is the reaction, which is the usual SIR model, and then there is the diffusion part, which is linear, because I assumed a linear diffusion term. Of course, if the coefficient D, S, I, and R depend on the state of the system, it's no longer linear. But if you linearize, it's again linear in some sense. But you change the matrix. But anyway. So, and now you have this matrix. If you remember, I told you at the beginning, if the network is symmetric, then the adjacent matrix is symmetric. And then also this matrix L is symmetric. But then if the matrix is symmetric, it admits an eigenbasis. So I can linearize the system. Here, instead of having a huge system where the Jacobian is 3 times the size of the network, here you can reduce the system to n times 3 by 3 matrices. So a very small system, each 3 by 3 system only depends on one eigenvector of the matrix L. One can also prove, because the matrix is symmetric, that the eigenvectors are real, and because it is a Laplace matrix, you can prove that they also are negative. It is 1, 0 eigenvalues, and all the remaining eigenvalues are 0. So you have a really good control of what happens, at least on the topological part of the network. So now you have to compute this the spectrum and understand how the topology of the network, so the spectral part, enters in the dynamics, so in the interaction part, and if the resulting Lyapunov exponent of the system is positive or negative. If this Lyapunov exponent is positive, then your epidemics will spread. But now if you look, because this Lyapunov exponent depend on the spectrum of the matrix L, you can look which is the node that are more involved in these eigenvalues. It is what's called localization. So you can have an eigenvalue, say, I don't know, -1, which is the most important, and this eigenvalue is only located in node J1 and 2. This means that the epidemics will spread only in city 1 and 2, not in the remaining one, at least at the beginning. Then it is the nonlinear part of dynamics, and then things can change, okay? But so I repeat, you linearize the system, you use the positivity, the non-negativity, non-positivity of the matrix L, the fact that it is a symmetric, then you can linearize the system, you can write an eigenbasis, and you can really completely solve the problem from an analytical point of view, understand how the spectral property of the network that are encoded in the matrix L play in the dynamics of the system. Okay, so I have not time to explain because I really need a blackboard to do all the computation, but I will show you some paper after that you can be interested in, and I'm glad to discuss with you if you want after or next days and so on. So now the next step, okay, I see that I consider a network, but indeed in reality, networks are not just one layer. If you think of transportation network, as I said before, you can use to move, you can go by foot, you can go by bicycle, you can go by car, you can go by bus, metro, flight, and so on. And so each way of transportation is a different level, because if you go by foot, you can meet a person around you, I don't know, at most 1 kilometer apart, not 10 or more kilometers. But then, so this is, you have a network of streets, if you want. But then if you go to the next step, buses, you can have networks where you link bus stops or nearby cities. If you go to the network of the train, you have faraway cities. If you go to the network of flight, you have very far apart cities or have a continent. And so each layer can be studied independently, and this is what we call now multi-layer network or multiplex. The example on the left is a social network where you have an agent which has both 2 accounts in Twitter and Facebook, and you can see if you only remain in the level of Twitter, the agent A and B can communicate, so they can exchange tweets, but agent A and C, they cannot communicate because they are not friends on Twitter. While if you know that there is also the down level, the one with the Facebook, you can see that A is indeed linked to C by the Facebook account. And so maybe because they are using this link, now A and C can also send tweets together or reply to one to the other. So taking into account several layers can help to spread the information, or if you want to prevent, then you have to cut the link that you want to use. So this is the second step that you can do. Once you have network, you can think of layers, and on each layers, repeat what I did before. The point is now that you have this matrix L each time that you have different layers. So if you have 3 layers, you have 3 times the 3 different matrices L, each one encoding a different network. So of course, things can be more complex, also get worse in some sense. Another possibility is the following. I consider now network as static network. I say there is a link between I and B, there is a street, there is something. But this is not true in general because links evolve in time. If you think of social networks, but the fact that I'm infected, maybe I will not I will not meet my friend. So the link between us is cut along, I don't know, 10 days, 2 weeks. Then the links is created again. Or if you think of phone networks, so-called, I can phone you, so during, I don't know, 10 minutes we are connected, but then when I stop the call, the network is disconnected. Okay, so now there is more and more evidence that the real networks are indeed temporal one. If you remember the fact that one of the first pictures that I showed you was the children in the school. This is a static picture, but if you look at different times in the day, maybe during the class time, you can only see links among students in the same class. But during the playground, you can see link among classes because this is different. So the topology of the network evolves in time. So here I show you 3 books, but there are more and more ones where you can study this temporal network, which is quite a recent topics, but I think is really important, and I think you have to take into account this if you want really to modelize epidemics, because it's really something which is taking into account time. So the time matters. Indeed, it can be shown that if you have a temporal network, you aggregate in some sense on a fixed network. I say, okay, I spent 1 hour, and so okay, my links weight 1 hour over 24, and so on. But the result on the projected aggregated network are not the same that on the temporal network. And this is clear because if I'm infected and during, I don't know, some days I will not meet anyone, I cannot spread. While if you collapse all the layers on the same one, but with some probability is one, I don't know, 1 week over 1 month, so 1/4, I can still spread the virus. So it's really a difference between aggregating and keeping the time slide of the network. Okay, so this is just a representation of temporal network, but I would like to show you that indeed temporal networks are multi-layers network, because you can consider that each layer is a time slice of my network. Okay, it cannot be too much short because otherwise all the links or the nodes are disconnected. But if you take, if you identify in your model an interesting or irrelevant time scale that can be 1 day for an infection, then you can aggregate all the contact during 1 day, then you have the second day, the third day, and so on. Then you can have slices, but these slices are the multiplex network, but now it takes into account the temporal evolution also. So you can really manage to bring together temporal and multi-layers network together. Okay, this is just to show you two recent papers, one of my group, another from another group, where we study the dynamics on temporal network. One paper, this on the bottom, is about epidemics. They study once you have 2 kinds of epidemics running on the same network, which is the role of the time evolution of the network, because this is really important. And the paper on the top is a paper of my group, where we study, okay, this Turing pattern, I have not time to discuss what they are, but this is a study how you have an equilibrium in a network, which is homogeneous, and how this equilibrium can be destabilized because of the diffusion. And here exactly we prove that if your network varies in time sufficiently fast, that you can have this non-homogeneous solution, while if your network is static or evolves very slowly, you converge to the equilibrium. So in some sense, in terms of epidemics, it means that if your network evolves fast, then you can have an endemic infection, while if your network evolves very slowly, then you can go to zero, so no infection at all. So this can be important in real epidemics. Okay, this is another paper. I think it was a preprint, but maybe now it has been published because it's 2018. Again, this is from a point of view of contact network. So where one node is a one person, again is epidemic spreading, taking into account temporality. Here, the important point is that usually once you do this epidemic spreading, you assume that if one person received the infection from someone before, all the possible paths are independent. This is not the case if the network is intemporal, because if you meet someone that once this person is infected, that you can get the virus. But if you meet someone once she is not infected, you cannot reach the virus. So the causality in the network impose a constraint on the epidemics, on the spread or the spread epidemics. Okay, now I think I have maybe 10 minutes. Maybe I can, maybe 5 if we am too long, so you can stop me.
No, you can go. You can
okay.
go.
So this is a really new stuff. Really means new in a few months, maybe less than that. Is going beyond networks. So up to now, I described network, all the kind, static, temporal, multi-layer, single layer, as object where you have two nodes connected by a link, because I say two units do interact in some way. And so the network can only describe binary interaction. Two persons interact. I spread the virus to you. I call you. I send a mail to you. But in reality, people interact in groups. If you think of social groups, it's very common that we are speaking 3-4 persons at the same time. We write papers, scientific paper, with 2, 3, 4 co-authors. Once you have a meeting, I'm not alone, I'm with other person. And so this interaction should be taken into account, because if you have 3 persons discussing, if one of these 3 persons has a virus, the probability that the 2 others get the virus is different if only 2 or one of them has the virus. And so what I would like to show you that is what is called high order interaction are really important. And so we have to go beyond this binary interaction and take into account that person can actually meet in groups of any sizes in principle. Okay, so to deal with this high order interaction, there are mainly 2 large groups of possibility. So I will switch on the light in my office right now. Because in Belgium, the sun goes down very fast. So there are 2 possibilities. One possibility, what is called a hypergraph. So hypergraph is you have nodes as before, but now nodes are not connected to binary groups, but to groups of any sizes. So now you have this hyper edge. So hyper edge is nothing but a set of nodes that are here represented with color. So you can have 3 nodes that are interacting together, isolated, and so on. So this is really a step beyond the network, because you consider any sizes of interaction. All the nodes inside the one hyper edge, you should not consider they are all the binary interaction. It's some sort of fluid. You have this group of nodes that
Timoteo? Olá. Estou tentando entender se é a minha internet ou lá
Acho que
fora.
foi a dele.
Ah, tá. Obrigada, José.
Ele
Por,
saiu
por um momento.
da sala, voltou.
Ótimo.
I lost my connection, sorry.
Sim,
Let me share again my screen.
sim. You were talking about hypergraph, very interesting.
Okay, so I was it. Okay, so I was saying that now you have nodes that are not connected binary, but are connected in groups of any sizes. And you don't have to think that three nodes in a group are three edges. There are really three nodes interacting. If you want, the difference is the following. Assume that I write a paper with three persons. This is an hyper edge, so really a collaboration with three persons. But I can also write one paper with you, one paper with him, you a paper with him. There are three binary papers. It's not the same thing because once we write a paper at three persons, we discuss with three heads. While if we write paper between two persons, there are only two persons involved each time. So the dynamics is really different considering hypergraph and networks. There is another possibility that is called simplicial complexes. The idea is the following. Here you have a stronger, if you want, a geometry of topology, where again, you can consider groups of nodes interacting together. Indeed, what is called a D-simplex is a set of D plus one nodes. But now you make the assumption that once you have, say, three nodes interacting together, there are the three-body interaction, but also the three two-body interaction are included. If you have a four-body interaction, so you have this diedra, so the pyramid, you have the four bodies, you have the four three bodies, and the four two bodies. So this is a more, if you want, you add some constraints, but these constraints are used to use a lot of topology. So while the hypergraph, you work at the level of set, so almost no topology at all. In the case of simplicial complexes, you really have topological object, algebraic one. And so you can use, say, D-bar operators, so boundary operators, you can study a lot of stuff. But of course, what you pay from one side, you gain on the other, and vice versa. So there are two different approaches. And so I will show you just two results on each one of those. So the first one is this paper, a recent one in 2020, where they study social contagion on hypergraph. And so the idea is really study epidemics, so social contagion, on hypergraph, so not on binary interaction, but take into account that people interact in groups. And I just highlight some few lines. And what is important is they find new transition. So they find the first and second order transition that were not present if you consider the binary interaction of the network. And also they find B-stability, which also is important because you can have several solutions, and hysteresis. So if you go back with a parameter, maybe you cannot find the same result that you find the first time. But this is really a recent paper where for the first time there is this social epidemics applied in the framework of hypergraph. And then there is the similar one for the case of simplex. So the title is Simplicial Model of Social Contagion. This is, I think, end of 2019. And here again, so they consider high-order model, but of course using these simplicial complexes. And they so take into account this structure. But as I told you previously, the fact that if you have a four-body interaction, then you need to consider all the smaller one. They restrict their studies to three-body interaction. Because you can understand, if you think of five-body interaction, there are all the four bodies, all the three bodies, all the two bodies. So the combinatorial explodes. So to make things simpler, here they stuck on the three-body interaction, but they show some interesting results. And so again, they find a discontinuous transition, which is only present if you consider this three-body interaction. And again, they have B-stability and this kind of new phenomena. So there are really phenomena that are related to the high-order interaction. There are really new results. If you are interested more in general on hypergraph, so I do some advertising on my result, I show you two recent papers of my groups where we study dynamical system on hypergraph. So there is not link with epidemics, but with generic dynamical system. Here we study synchronization, if you're interested, how oscillator, linear and chaotic one, can synchronize if you consider interaction with multi-body. And the second paper, the one on PRE, so the one on the bottom, is a random walk, so a simpler diffusion problem on the hypergraph. But again, we show that this process is different from the same process that you have on the network. And okay, I think I'm finished with this. I hope you enjoyed the talk, and if you have any question, I'm here.
Very, very, very interesting. I think we have to
put my headphone because now it's raining in Belgium. So Belgium is the country where you have 4 seasons in the same day. Before it was sunny, now it's raining. So, okay.
Yes, very interesting. As you remember, as we talk in May, the simplicial complex, unfound the simplicial complex. Maybe we have to talk. We have to talk again. We have to make a. Actually, I spread the simplicial complex notes that we had in the physics. The physics now are getting fonts of simplicial complex.
Yeah, all the papers that I show you are from physics, indeed. Yeah, I think if simplicial complexes were known by mathematicians that do optimization and so on, and now physicists can use them more and more.
Yeah, and definitely even the hypergraph, this notion, because if we think about Brio, we have this community. So you have things, you have community mixing, and then you have people from the community going to another community. You have not more than a person, you have the community dynamics. And I think even more when we think about COVID and viral charge, because you have to put together enough people to have that critical viral charge.
Yeah, because I think there is also, when you have more persons together, they change their attitude, their behavior. And so there is a social attitude that promotes, in some sense, the virus spreading. So I think the high order interaction are really important.
Yes, definitely. So we definitely have to go back and make an effort to make to talk more. Now that we have a group of students, they're very animated. We have Jose that is more on network and making a connection to DNA, but he's interested in general. And we have even we have a 4th student there.
Okay.
So Armando, your question? No, people. There are so many things, very rich.
Yeah, it was a lot of material a few times, so I'm sorry.
No,
not a question, but a comment as you talk about this beyond networks. I thought that's complex, so I'm just trying to understand the networks. But something you did not talk about, but might be some compromise between networks and something beyond, would be weighted graphs, weighted networks.
Yeah, this is true, but the point is, how do you introduce the weight? And in one of the papers that I show you previously on my groups, for instance, this one, the random walk, what you prove is the following. You start from doing a random walk on a hypergraph, but then there exists a standard network where you can project your dynamics, put in the right weights on the network, and then you have 2 systems that are equivalent from a dynamical point of view. So what you say is true. You can use something between networks and high order or hypergraph. This is a weight network, but then you have to put, in some sense, in the right way the weights. You cannot just put them by some random or some personal choice. because otherwise the dynamics will be different.
Yes, of course. I thought, for example, that these groups might have large weights among them and smaller weights with other groups, something that's not that random, for sure.
Yeah, no, of course, I would say random, say without any insight from the dynamics, because large among them and weak between them, okay, you have to define the large and weak, but I agree with you. There is this intermediate scale, yeah.
Timoteo, you can send some of this article because sometimes it's...
Yeah, I can send you the PDF of my talk with all the papers. Yeah, okay, no problem.
And this one by Hypergraph and Simplicial.
Yeah, also the papers that are not from me. I have all the papers that I quote, so I can send you everything.
Yeah, so if you send that, it's easier. We have a Google Classroom, I can put it there. So it's easy for people sometimes. Okay, so very, very interesting. Thank you very much. And
thank you to you.
And I hope we do soon have a personal chat.
Okay.
I want to share,
also, if the other person that attended the talk tomorrow, they will realize that they lose something and they want to ask a question, do not hesitate. I think Stefanella shared my email, so you can contact me.
Yeah, and actually there are a lot of people that have classes at the same time. So we don't have this phenomena that more people are watching in the afternoon. Yeah. So this is why I put it in the course web page, because we observe this phenomena there.
But I did the same with the previous talk because I was unable to listen to them at the time. So
yeah, so we do have it, but thank you very much.
Thank you.
And next, we will have also, maybe this is interesting you, we will have in the future Nathan Kutz, and next Thursday, they will give a mini course on data. So maybe, yes, this might, if your students, your postdoc, whatever, you're welcome.
Okay, thank you very much.
Okay. So thank you.
Bye.
Bye.
Bye. Bye.
You. Bye.
Bye.